Welcome to the structural analysis course. So in the last class onwards, we have started the energy method of structural analysis. So in this method, we are more focused on calculating the displacement and slopes in a beam or maybe in a portal frame or truss in in any structure using the energy method of equations. So in the before energy method, we discussed about the geometric method. Using the geometric method, how exactly we can calculate the slopes and deflection in a beam or maybe in a truss. So in the last class, we have derived the basic equations, that is strain energy equations in a beam if a external load is acting on a structure. So in this lecture, we'll discuss the Castigliano's theorem to calculate the slopes and deflection in a structure. So let's get started. So if you recall, last class we have discussed what is actually the strain energy or what is basically the energy equations. So as if we apply any load, so if you consider this is a beam, this is a simply separate beam, right? Fire end is single, one end is single, one end is hinge, another end is roller, and some many external loads are acting, p1, p2, p3, maybe it may be udl or uvl, whatever it may be, the load is acting. These are the external loads acting on a structure. So you can consider this as a portal frame also, or it may be truss. You can consider any structure where the external loads are acting on a structure. So because of the external load acting, our beam will deflect, right? So this is the deflected shape. If you see this curved line, blue color line is basically the deflected shape after application of the load P1, P2, P3, dot dot. So now, as we are applying the force externally, although this extra force was earlier not there in a structure, we've applied them externally. So basically, we have induced some extra energy into a structure. So earlier this was the beam, there was no external force, but after application of the external force, basically we have induced some extra energy from the outside. So this extra energy, we call it as external energy, and this external energy will be stored inside the structure as a strain energy. So that's what we discussed in the last lecture in details. So this strain energy will be stored into the structure or in a beam or column, whatever it may be. So that strain energy, we call it internal energy. So because of external energy, internal energy is developed or stored inside the structure. So as per the conservation of energy equation, we can't create energy or we can't destroy energy. So because of that, whatever load will be applied, that is whatever external energy will be given to the structure, so that external energy will be stored inside the structure as the internal energy, and the magnitude also will be same. So whatever external energy we have done, we have applied, the same amount of energy will be stored into the structure as the internal energy. That energy we call it strain energy. So now that is the basic discussion we discussed in the last class, and we have derived if a point load is acting, then how much a strain energy will be developed inside the structure. Okay, so anyway, so this is our first Castigliano's first equation to find out slope and deflection of a structure. So that is our main objective. That is, this is the deflected shape of a structure. After application of load, the deflection happened. U1, U2, U3, different point, different deflection happened, and similarly, slope also changing at the different point. So our main objective is to find out the slope and deflection using the energy method. So you can appreciate that energy method is very much useful when you have the complex types of loading. So if any one or two UDL is acting, or maybe point load is acting, in that case the geometric method, what we discussed, three methods in the geometric method we discussed in details, so that method can be employed. Whereas if any complex type of loading is acting, for example multiple loads, multiple point loads, 1 2 3 like that, and dot dot, and many types of point loads are acting, and maybe UDL, UVL, many combinations of loads. That is, in real structure, if you see, loads are not symmetric or not maybe simplex. There may be complex loads are acting on a structure. So in that case, geometric method may be difficult. Using geometric method, it may be difficult to solve the structure. So in that case, energy method will be very much useful for that. So first we'll see what is the Castigliano's first theorem. So for a linear elastic structure, when the external force only cause deformation, so this deformation, whatever has happened, that is because of only external force. Earlier, if you remove this force, the beam will become going to its original position. right? So whatever deformation happened, that is only because of the external force. So where the external force only caused the deformation, the complementary energy is equal to the strain energy. So whatever energy is applied externally, that will be stored into the structure as a strain energy. For such structures, like for this type of structures, maybe this deflection may be happening because of temperature also. Sometimes in the summertime, maybe because of high temperature, the material expands. So in that case, the beam or column or maybe frames may get deformation little bit. So in that case, our Castigliano's theorem may not be applicable, because that deformation happened because of temperature, not because of external loads. So this theorem is only valid when the load is external load is acting. Although we can incorporate the temperature effect and all, but proper formulation is required for that. So for such structure, the Castigliano's first theorem may be stated as: the first partial derivative of a strain energy of a structure with respect to any particular force gives the displacement of a point of application of that force in the direction of its line of action. What is this theorem? This theorem says, so whatever strain energy will be developed into the structure, if you take the derivation, that is the partial derivation, if you take the first partial derivation of the strain energy of a structure with respect to any particular force, P1, P2, or any particular force. For example, you want to find it out deflection at this point. So in that case, the partial derivative of the strain energy of entire beam strain energy will be taken with respect to P2. For example, this is P2. Okay, so whatever strain energy partial derivation we have to take, that is with respect to P2. So where we are finding out the slopes and deflection, in that point, whatever loads is acting, so we have to derivate the strain energy with respect to that force only. So give the displacement. So if you take the derivative of the strain energy with respect to that force at that point, that will give you directly the displacement of that point in that direction. So that is our Castigliano's first theorem. So that is first theorem is related to how you can calculate the deflection in a beam. Now if you want to find out slope also in this point, so let me just draw it here. So now you want to find it out the slope as well. So slope is nothing but like that. So how much angle it makes with the horizontal, that is nothing but a slope theta, right? So this theta, now if you want to find it out, so in that case, what we have to do is we have to take the derivative, that is it may be first partial derivative of strain energy. We have to do it with respect to any particular force. If you do it, for example, here force is acting P2. So if you derive the partial derivative with respect to force P2, then we'll get what is the deflection here, U2. Okay, so whatever you get, that is U2, will be given to us. So next, now if you want to find out slope, theta 2 maybe at that point. So in that case, what we have to do, we have to take the derivative with respect to moment, and then whatever we will get, that will be the slope. So very simple. First theorem says, if you take the partial derivative of a strain energy with respect to force at that point, that will give you displacement u1. And if you take the partial derivative of a strain energy with respect to moment at that point, that will give you directly the slope. Very simple and very elegant way to solve the slopes and deflection in a beam. So now let's see the derivation little bit. So if you recall, last lecture we have discussed whenever the load is applied in a structure, external loads are applied in a structure, our structure gets deformed. So this is a deformed shape, this curved line, blue color line. So if you see here, deflection happened y1, u1, u2, u3 dot dot, many total maybe n number of loads are acting. So total u1, u2, u3 dot dot, n number of deflection will be happening at the different points. So what is work done? Work done is nothing but a force into displacement, that we call it work done. So how much work? So here, what is the deflection happened? Deflection happened u1. Similarly to result, how much force applied here at this point? It is p1. So because of the deflection happened u1, so total how much work done happened? Work done is nothing but energy. How much external energy we have put into the structure? So that will be simply force into distance. So distance is u1, we know that is deformation happened u1, and force is p1. And that too, if you recall, last class we have discussed this p1, all the forces are not acting suddenly. These forces p1, p2, p3, all forces acted gradually. So maybe at the beginning of the time there was zero force. So if you I just draw it. So this is the force displacement diagram of each beam. So maybe this is force P and this is deflection U. So the force entirely at the time zero, it does not happen at not suddenly. So gradually we applied, gradually from zero onwards we applied forces little bit, and after some time it reaches to the value of P, and we got the final displacement also U. So whatever energy, external energy will be given, that will be simply the area under this curve. So area of this triangle is how much? Half into base is U into height into P. Right? Half into U into P. So that is the work done, or external energy is applied into the structure. Half into P into U. Okay, so in other words also we can tell that, so the deflection happened is U, and how much load is applied. Load begin at the beginning it was zero load, but gradually we applied the load up to P1. So what is the average load? Average load will be 0 plus P1 by 2, simply P1 by 2. So force is P1 by 2 and the deflection happened is U1. So in that way also we can calculate what is the total energy, or total what is the external energy happened. So anyway, so external energy because of this P1 is half into P1 into U1. Half into P1 into U1. So that's what is written. W is a external energy, which is nothing but half into force is how much? P1 at that point, at this point, and the deflection is U1. U1 deflection happened. So that is because of energy stored because of first load P1. Now we have the P2, P3, all Pn loads are acting. Then this will be plus. So what is the total external work done happened? Half into P1 U1 plus half into P2 U2 plus dot dot, all the forces will be coming, plus half into Pn Un. So this is the total external work done into a structure. So as per the conservation of theory, conservation of energy, this entire energy will be stored as an internal energy also. So whatever external energy is applied, that is this much. Uh, so whatever is the external energy applied, that is work done W, that is nothing but stored as an internal energy, capital U, or we call it strain energy into a structure. So whatever external energy we have applied, so this is total work done externally applied, so the same amount will be stored in a material inside the beam as an internal energy U. That is our conservation of energy theory, right? So W is the external force, U is the internal, so both are same. If you see the same equation we have written here also, because the force and the whatever external energy is applied into the structure, that will be stored, same amount will be stored as the internal energy U. So now what is U? U1, what is U1? Small u1. This capital U1 is internal energy. But what about small u1? U1 is nothing but deflection at here. U2 is deflection here, like that happening. So now, what is U1? So U1 is deflection under the load P1, right? But U1 is not caused because of only P1. U1 caused because of P1, P1, P2, P3, all the loads acting on a beam, right? So because if you apply here P2, so because of only P2, if it is applied, then also you will see some deflection happened under the at this location also. So that is whatever net U1 deflection happened, that U1 is responsible, is due to all the forces acting on it. So that's why U1 can be written as A11 P1 plus A12 P2 dot dot, means U1 is nothing but the deflection at this point. So this is nothing but the this is nothing but some portion of P1 plus some portion coming because of P2, some portion coming because of P3, like that. So what is now A11? A11 is a flexibility constant, we call it. Flexibility constant means if you apply unit load here, if you apply 1 unit load at this point, how much deflection happened here, that term we call it A11. Similarly, if you apply so that is A22, A12. A12 means at location 1, this is location 1, 2, 3, like that it will go. So at location 1, because of location 2, if you apply unit load is applied at 2, then how much deflection happened here, that we call it A12. Similarly, you have A13. A13 means 1 means in the first location, means in this point we are talking, and 3 means at third position. If we apply a unit load, then how much deflection happened at first position, that we call it A13. Like that, these are all flexibility constants are there. So this is U1 is nothing but the combination of all forces, the whatever deflection happened, that contributes all the forces. Similarly, if you do it in respect to I, then I, if you replace 1 with I, that is in general equation we have written, same U as a general equation. So now if you substitute the value of U1, U, U1 here, so U1 already we know this is the part. If you substitute this U1 value here in this equation, what will you get? U1 equal to half into P1 into this entire term. This entire term of U1 will be written here. Similarly, now you have the half into P2 into U2. Same half into P2 into U2. This U2 expression also we can be written as a very big equation. Something. So all the U1, U2, U3 values are substituted in the main strain energy equation. This U equation we substituted all U1, U2, U3. So now this is our final strain energy. Now what is Castigliano's theorem tells? Now if you take the derivative, partial derivative of a strain energy with respect to the force of any at any point. So at this point, let's consider this point first. So here this is the total strain energy equation. Now if you derive this equation with respect to P1 at this point, so del U by del P. So this is a partial derivative, that's why the symbol is del U by del P1 equal to, now if you take derivative of this entire part, what will happen? So half into P1 A1 anyway, so if you just multiply both, what will you get? Half into P1 square A11. So now if you integrate P1 square with respect to P1 we are deriving, so you will get, okay, let me do it here. So if only this portion I'll do it, so what will happen is half into P1 square, P1 square A11, right, plus half into again P1 P2 A12 plus dot dot. So this is the first part, first term we have written. Now similarly from this part also will be coming here, like that the entire segment will go. So now if you derive it with respect to P1, then what will you get? So P1 square 2 will come out, so 2 will be cancelled out, so only remain part is A1 1 P1. Similarly from other part also this equation, similarly other part P, that is other, or wherever P1 is not there, it will go to 0, right, because we are taking with respect to P1. So this is first term will come. Now from the next term, so from here, so half into P1 P2 A1 2. So P1 anyway, because we are taking with respect to P1, so P1 will simply go away, so we'll get only P2 into A12. Similarly, all the parts, all the strain energy differentiation for all the part will be taken care, and the final expression you will get something like that. Del U P1 is equal to A11 P1 plus A12 P2 dot dot. Now, can you recall what is this one? This one is nothing but this U1. If you see what is U1, A11 P1 plus A12 P2 plus dot dot. Same thing we got, A11 plus P1 plus A12 P2 dot dot. So same thing both. So this is nothing but U1. So this entire part is nothing but U1. So that is our Castigliano's first theorem. That means if you take partial derivative of a strain energy, so U is a strain energy, and if you take partial derivative with respect to the load at P1, so whatever we get deflection U1. So very simple theory, and this is a proof of the Castigliano's theorem. So at any point, now for example, if you want to find it out, what is the deflection U2? So in U2 basically then we have to take the partial derivative with respect to P2, whatever load is acting here. So if you take the partial derivative of with respect to P2, then we'll get the what is U2. Now P3, if you take P with respect to P3, we'll get the U3. So like that, this entire expression will go, and we can easily compute what is U1, U2, U3. This is deflection at any point we can compute. So that is about the deflection. Now what is Castigliano's second theorem tells? Second theorem tells if you want to find it out slope also. Our main objective is to find out deflection and slope both. So deflection, we know how to do that. Now let's do it for slope. So for slope, this entire strain energy has to be derived with respect to moment m1. For example, you want to find out slope deflection, the slope at this point. So in that case, the derivation has to be taken with respect to m1. If you want to find out here, then with respect to m2 we have to do it. So whenever if we take with respect to moment, we'll get the slope at any point. So that is our Castigliano's theorem. Two theorems. So now let's solve a quick example, then this concept will be clear to you. So what is the question? Find the displacement and slope at a tip of the cantilever beam. This is a cantilever beam, and at the tip P1 we have to find it out. Assume the flexural rigidity of the beam EI is a constant. So very simple problem. We have solved this problem in past with geometric methods. Now we have to solve this method with respect to energy method, that is Castigliano's theorem. Using that, we want to find out what is the deflection and slope happened at A. So this is a cantilever beam, simple cantilever beam, and the load is applied. P is applied at the tip. Now our objective will be to find it out what is the slope and deflection at the end A. So first we write what is the moment happened. So just take a distance x, arbitrary distance. Let's do it. So take a section here which is at a distance of x from the left hand side support. Then, or maybe we can take it as a right hand side support. Let's do it here. So at a distance of, oh sorry, x is already given written here, no need to draw. I'll just remove this, already there. So this is our x, which is at a distance of x from the point of action where loads are acting. Now our objective, so first we'll write what is the moment equation. So moment at a section which is at a distance of x from the load will be simply minus p into x, force into distance, right? Force is p and distance is x, so minus px, because it is a clockwise direction, minus. This is our moment. And the strain energy stored in a beam due to the bending, we have derived this expression in the last class, where if because of bending, how much strain energy is stored into the structure. That was integration 0 to L m square by 2 EI into dx. If you recall last class, please visit. We'll see. You can understand that how we got this expression, m square by 2 EI into dx. So now if you substitute m value minus px into here, so this expression you got it. Now if you take the derivative, so what is Castigliano's first theorem tells? Castigliano's first theorem tells if you take the derivative, first derivative, partial derivative of a strain energy with respect to the load at that point, then you will get the what is the deflection here. Means this is a total strain energy. So this strain energy, if you take the derivative, for example, our main, what is our question? Question says to find it out the slope and deflection at the tip, means here we have to find it out. So whatever total strain energy is stored, that has to be derived with respect to the force at that point. So force is how much acting, p is acting, right? So this total strain energy has to be derived with respect to force p. So now if you take the derivative with respect to p, what will you get? So here is p square l cube by 6ei, so 2 will come out, so you will get simply p l cube by 3ei. If you take the derivative with respect to p, then you will get pl cube by 3ei, which is nothing but the deflection at a. Over. Very simple. So uh, first we have to write our strain energy equation. So once we write strain energy equation, just we have to take the derivative with respect to the force. If we are finding out the displacement, then this will give you directly displacement. So this is displacement at point A. Over. Problem solved. Partial problem solved. So now next our objective is to find the displacement as well as slope also at the tip, right? So for finding out the slope, total strain energy has to be derived with respect to moment. But here if you see at A, there is no moment is acting, only external force is acting, P1 P. So that's why we derived our strain energy and we got our final expression. But to find it out the slope at that point, we have to derive the strain energy with respect to moment. But here no external moment is acting here. So what we'll do is we'll apply a fictitious moment, imaginary moment we applied, m naught. Although this m naught in reality it is, there is no moment here at this point, but we have to take the derivative to find out the slope, right? This is the as per the Castigliano's theorem. So that's why we apply a fictitious moment, that is a imaginary moment we applied at a m naught. And now we can find it out what is the total strain energy in the beam, and then if you derive it, the strain energy with respect to moment m naught, then we'll get what is the slope at this point. So to find the slope at free end, we need to differentiate the strain energy with respect to externally applied moment m at a. That is our theorem, but there is no external moment, right? So that's why we apply some imaginary moment m naught. So as there is no moment at a, apply a fictitious moment m naught at a. Now moment at any section at a distance away. Now if you find it out what is the moment at any distance. So here we have written it m equal to minus px. Now we applied extra m naught. Now find it out what is the moment generated here at distance of x. That will be minus px already because of moment, because of this load p into distance px, minus again we applied a imaginary moment, that is m naught. So again px minus m naught. So this is now our moment at a fixed at a distance x. And now total strain energy will be integration 0 to L. So our expression is same, minus m square by 2ei into dx. So here m value is this entire part. So that's why this entire part square by 2ei. Now if you take the derivative, two portion will be there. And the okay, so we have divided, we just simplified it, and this is our final expression. So now in this strain energy equation, we have to derive it with respect to m naught to get the slope at a. So if you do integration derivation with respect to m naught, this expression, what will you get? So here there is no m naught, entire part is constant, so this will vanish. So here m naught is there, so m naught will go, so only you have the pl square by 2a if you take the derivative with respect to m naught here. Similarly this portion also, m naught square is there, so 2 will come out, so you will get final expression m naught l by ei. So this is the final u expression. So that is nothing but theta I, right? Whatever, if you take the derivation with respect to m naught, whatever we'll get, that is our theta I. But m naught is a fictitious moment, right? In general, in reality, there is no m naught. In reality, m naught is nothing but a zero. M naught is nothing but zero. In reality, we just applied fictitiously, just imaginarily we applied this road. So now substitute here in this expression m naught equal to zero, because in reality there is no m naught. We applied externally. So what we get, final expression will be m naught, so this term will go away, so we'll get pl square by 2ei over. So this is the slope at a, and this is the deflection at a. So at any point now we can find it out what is the slope and deflection with respect to the, using this method. So just write the strain energy and differentiate it with respect to the point load where it is acting. So for example you want to find out what is the deflection happened at the middle. Although middle there is no force is acting, right? So but we have to derive this with respect to the force at that point. So what we'll do, we'll just apply imaginary load, maybe p1 or p2 or whatever it may be. We apply a p1 p2 or any imaginary load at that point, we write the moment equation. Similar process we'll do the integration with respect to p1, and then at the end we'll substitute p1 equal to 0, because in reality there is no p1, right? So we just substitute p1 equal to 0, then whatever final expression you will get, that is the deflection at that point. Similarly, slope also can be calculated at the any point. So using this method, very quickly we can compute the slope and deflection by just writing the energy equation and taking the first derivative. We will get force and slope and deflections. Thank you.